Hi, thank you all for being here today, and thank you, Lily, for being here, you today presenting your work. So Lily Blaiset is now a postdoc at Université Paris-Cité ESPCI, and she recently finished her PhD, and she's now doing a short postdoc looking for jobs. Am I right?
Yes, exactly. So I'm doing a postdoc for a few months, and then I'm trying to have a position in the industry in the cosmetic field in the research.
Nice. And so just a few questions about your career. Where did you do your bachelor's and master's? And so now you've just finished your PhD and you're doing a postdoc in Paris. So is it the same place where you did your university studies?
No, so actually I did my engineering school in Bordeaux. So it was in Bordeaux INP, and I studied physics and chemistry there. And then I moved for my PhD in Paris, so working with the MSc lab with Elisabeth Guazelli, Mathieu Rocher, and with the Sim lab at ESPCI with Nicolas Sanson. And I studied. So when I was in my engineering school, I did an internship on the rheology of aerosol bases, and that's why I ended up doing my PhD on the rheology of dense suspension, which you will see in a few minutes. And now, I'm finishing. I'm doing my postdoc to finish to publish papers, basically.
And how did you find your PhD? And
I found it actually by like on the CNRS website, and then I discussed with Elisabeth Cozelli and Nicolas Sanson. So I had an interview with them, and I discussed with my. So I had sort of a. So when I was in Bordeaux, I had some teachers that knew those researchers, and after a discussion, we kind of agreed that it was a good choice for me.
okay, now the hard question, why, I mean, there's no comment behind the question, but why industry, not academia? And how long, I mean, is it something that you already knew before?
Yes, I think I already knew that I wanted to come back to the industry. So actually, I did all of my engineering school internships in the industry, and well, I during my PhD, I still wanted to discover a bit of the academic world. But I don't know, I think I like working on, let's say, uh, more concrete products. I don't know how to say
Yeah.
really, but yeah, I don't know. I think it's a different dynamic, and I would like to continue in that way.
So the PhD didn't change your mind.
Not really. I mean, no. My supervisors wanted me to do a postdoc, but I negotiated only for a few months and then coming back to the industry.
Well, good luck with that then.
Yes, thank you.
Okay, if people in the audience want to ask questions, feel free to do so. Otherwise, I think we can start the presentation.
Okay.
And in general, I would say that if you have questions, please raise your hand. You have the option on Zoom. Otherwise, you can also write questions in the chat, and we will keep the chat. We will look at the chat to interrupt Lily as there are questions. Is it okay for you, Lily?
Yes, of course.
Okay.
Don't hesitate to interrupt me.
And I think you can start sharing your presentation. It should stop mine.
Okay. So I guess I do this.
Yeah.
So can you all see my screen and my laser pointer?
Yeah, perfect.
Okay. Okay, so welcome everybody, and I thank you for attending this presentation. I'm pleased to present you today a part of my PhD project that I just finished recently, and this will be on the friction in dense suspensions of particles with tunable properties. This PhD project was an experimental study on the impact of microscopic properties of particles on the macroscopic rheological properties in suspension. And as I said, this project was in partnership with two laboratories, so the MSc lab from Université Paris-Cité and the SIM lab from ESPCI. So, I tried to. Okay, it works. So let me briefly introduce you to the context of this project. Of course, suspensions are ubiquitous in our environment, and especially in the industrial field. And a suspension can be seen as an effective fluid. What the parameters that we like to define usually are the volume fraction, which is related to the solid and liquid content of the suspension, and the relative shear viscosity, which is related to the suspension viscosity and the fluid viscosity. So historically, suspensions have a relatively old background because it started in the beginning of the 20th century with Einstein, who established a theoretical law linking the relative viscosity to the volume fraction. And this law is valid for fractions under 5%. Then you have the semi-dilute regime. So Batchelor and Green added a term, so phi squared, to this equation because they took into account the hydrodynamic pair interactions, and this law is valid for volume fractions under 20%. And as for more dense suspensions, more concentrated suspensions, we don't have any theoretical law. But what we have is this nice graph that comes from Guazzeli and Pouliken. And what they did is reviewing all the experimental and simulation data obtained on non-Brownian dense suspensions. And this graph reports the relative viscosity as a function of the volume fraction. And what we can see is that you have two branches appearing with different critical volume fractions, so that are dependent on either the polydispersity, the particle shape, and the particle nature. And at this jamming transition, actually, so these two branches correspond to two different states of the particle. One where the particles are in contact, so the microscopic friction coefficient mu p is positive, and the other branch where mu p is so the particle are not in contact. And these two branches can actually be represented by those two branches. One is the frictional branch, the pink one, and the other is the frictionless branch, where you have two different critical volume fraction. These branches can be related to a phenomenological law, and it links the relative viscosity to the critical volume fraction phi c and an exponent gamma. And it has been found that for frictional particles, so particles in contact, phi c will be between 0.52 and 0.6, and the exponent gamma is equal to -2. And this has been shown experimentally and also by simulation work. For frictionless particles, we have very few experimental work, actually, but we have simulation work and theoretical work that have shown that the volume fraction is approaches the random close packing fraction of a suspension, and the exponent gamma approaches -2.83 according to the theory of the Julian. So actually, when we characterize a suspension, it is important to remember that the mixture is made up of an incompressible liquid phase, but the particle phase can be compressible, and it expresses dilatancy when we increase the shear rate. And in result, we can define a particle pressure, PP, which is dependent on the normal viscosity of the suspension and the shear rate. And with this definition of the particle pressure, we can define the macroscopic friction coefficient, mu, which is the ratio of the shear stress divided by the particle pressure. And it has been shown that this macroscopic friction is a signature of the microscopic friction. And this parameter can be more easily measured. And actually, I will show you how we can measure it. But first, I want to present you. Yes, so actually, this paradigm inspired a lot of new configurations, which are related to pressure-imposed rheology. And what I want to show you is a little comparison between conventional volume-imposed rheology and the pressure-imposed rheology we used during this PhD project. So in the conventional rheology, we control the following parameters, which are the volume fraction and the shear rate, and we measure the parameters, the shear stress and the particle pressure. However, when you use a commercialized rheometer, you cannot really measure this particle pressure. We don't have the devices to do it. Nonetheless, you have these constitutive laws with this volume imposed rheology, and you have the shear stress and the particle pressure depending on the volume fraction and the shear rate, basically. And if we look at these laws in the pressure imposed configuration, well, this time the control parameters are the particle pressure and the shear rate, and the particle pressure is usually imposed by a grid that lets the suspending liquid pass, but not the particles. And the measured parameters are the shear stress and the volume fraction. By analogy with the dry granular community, we can introduce a viscous number, J, which is basically a normalized shear rate. And the constitutive laws that we obtain for the pressure imposed configuration is the shear stress, which is related to the particle pressure, and we see that that we can measure through this shear stress the macroscopic friction coefficient and the volume fraction, and both are dependent of this viscous number J, so the shear rate. So yes, before going into the results, I would like to introduce you two different configurations in pressure imposed rheology that we used for this project. And the first one being the capillaritron rheometer. So this was a device developed in Marseille by Bruno Etcheverry et al. And I won't go into much detail, but basically we can impose the particle pressure by controlling the capillary interface of the suspension in the device. And we can impose a wide range of particle pressure. And another important thing is that in this configuration, when you are close to the jamming point of the suspension, the macroscopic friction coefficient follows this law, and we have a parameter mu c that I will talk about later, and also an exponent mu alpha mu, sorry. And you have the expression of the volume fraction, which is dependent of the critical volume fraction, and an exponent alpha phi. So we used this device during during my PhD, but this device can be quite complex to use. So in parallel, we developed in another configuration that is also pressure imposed, which is the rotating drum. And this rotating drum allows us to measure the avalanche angle of a suspension in the quasi-static regime. So this setup functions as such. You place the particles immersed in a Newtonian liquid, and you let the particles sediment. And after rotating the suspension at a very low speed, there is an avalanche angle appearing. And this avalanche angle is directly related to mu c, which is the quasi-static macroscopic friction coefficient. So we measured this parameter, and it is important to remember that in the rotating drum setup, we are in those following conditions. So we are at a low viscous number in the quasi-static regime, and we impose a low pressure, which is about 0.1 Pascal. So now that I've given you that I've presented you the different devices that we used, I want to come back to our motivation for this work. So our goal was to tune the macroscopic friction in non-Brownian dense suspensions. And these are the different problematics that came out by looking at the literature. So first, we noticed that there is a lack of experimental work on dense frictionless suspensions. In the conventional rheology, so in the volume imposed configuration, it can be difficult to assess consistent measurements close to the jamming transitions. And also we wanted to assess the role of surface force interactions on the suspension flow, so at the macroscale. And to do this, we designed stimuli responsive non-Brownian particles. Then we characterized them using the two devices in pressure imposed configurations, and we correlated these results to nanoscale surface properties. So the rest of the presentation will follow as such. I will briefly present you what kind of reaction we use to make these stimuli responsive non-Brownian particles. Then I will present you the results in the quasi-static regime and the correlation we made at the nanoscale. Next, I will present you the dynamic measurements done in the capillarytron, and we will finally conclude and see the upcoming perspectives of this project. So beginning with the reaction used, what we did is we took polymethyl methacrylate particles, so PMMA particles, that were cross-linked and monodisperse. They have a relatively high Young modulus, about 3 to 4 gigapascals, and these particles are hydrophobic, so they don't swell in water. These particles undergo an alkaline hydrolysis, and basically they are put under relatively high temperature with potassium hydroxide, and we obtain polysodium methacrylate particles at the end, which are stimuli responsive, and they have a relatively lower Young modulus, 1 to 2 megapascals, and they become hydrophilic. So what we did first with these two batches of particles is that we compared them in the quasi-static regime. So to do so, we measure the avalanche angle of those two suspensions in pure water. And here are the results for the PMMA particles. So these particles have a diameter, are non-Brownian because we have a diameter of 60 microns. And the avalanche angle versus time is on this graph. And we recover the average avalanche angle of this suspension and the resulting quasi-static macroscopic friction coefficient, mu c. So the two values of theta c and mu c are very typical of a frictional suspension. However, when we look at their hydrolyzed version, so their hydrolyzed version have double in terms of particle diameter, so they are 120 microns, but they're still monodisperse. So when we measure the avalanche angle of this suspension, we obtain a much lower one, and thus a much lower mu c as well. And these values are more typical of a frictionless suspension. So when we chemically modify the PMMA particles, we obtain a frictionless suspension. Why? Well, if we look at the so actually, if we look at the surface topography of our particles, and to do that, we performed AFM liquid measurements in pure water. So basically, we glued particles on a substrate, and we immersed them in water, and we assessed the apex, the topography of the apex of the particle. The quantitative value that we measure is the surface roughness. And so you can see here the images and the height distributions below. And if you look at PMMA particles and their hydrolyzed version, actually the surface roughness that we measure for the hydrolyzed particles is higher than the one of the non-hydrolyzed version. And if we look at the intrinsic properties of the polymer, well, this difference of roughness can be explained as such. So if you have PMMA particles, you have actually a hydrophobic polymer, and the particle will be directly in contact. They don't swell in water. So the roughness you measure is let's say, the direct asperities of the particle. However, when you have a hydrolyzed PMAA particle, you have a polyelectrolyte backbone, and this polyelectrolyte swells in water and can expand in water. So the the roughness you measure can be considered as a polymeric layer that expands in water. And this actually provides electrosteric repulsions since you have high roughness and negatively charged backbone. And this electrosteric repulsion is at the origin of this frictionless state of these particles. So they kind of, this induces a lubrication between particles. So now that we know that we have electrosteric repulsion, we want to know how this behaves in presence of salt. So the first salt that we studied is a monovalent one, which is sodium chloride. And what we did is put these hydrolyzed particles in different concentrations of sodium chloride, and we measured the swelling behavior of the particles and the avalanche angle of the same suspension. The results we obtained are the following. So you can see the graphs here of the particle diameter and the avalanche angle as a function of the ionic strength. And so the gray lines you can see here are the results reported for PMMA particles in pure water, and the blue lines are the ones of the hydrolyzed particle in pure water. As you can see, the particle diameter decreases slightly and the avalanche angle increases. So you have less swelling properties and an increase in theta c, so consequently in the macroscopic friction of the suspension. To understand that, we continued to do AFM measurements under liquid environment, and we changed the concentration of sodium chloride in situ during our measurements, and we measured the topography of the apex of one same particle. So the image you see here is the same particle, and as you can see, the topography seems to be smoothed. And if we plot the surface roughness as a function of the ionic strength, we can see that the surface roughness decreases following a power law with an exponent equal to approximately minus 0.28. Actually, this kind of behavior has been observed for individual polyelectrolyte brushes, which have a well-defined brush length. And this comes from the work of Pincus et al. So in their work, they defined or they observed two different regimes. One is the osmotic regime, and the other is the salted brush regime. So in the osmotic regime, what you observe is the polymer chains are strongly extended in the solution, and this is due to the interaction with very few counter ions present in the solution. However, when you approach the salted brush regime, the salt concentration in the solution neutralizes the polymer charges, and as a result, you have the electrosteric repulsion that is screened as the concentration increases. So here we do not measure a precise polymer brush length because we measure the surface roughness, but however, we can still notice that this roughness seems to vary like a layer of well-defined polyelectrolyte brushes in the presence of a monovalent salt. As you can see, theoretically, the polymer brush length varies as a function of the salt concentration to the power of minus 1/3, and we found an exponent to minus 0.28. So these observations are pretty close. And this shows that while increasing the salt concentration, we screen this electrosteric repulsion, and we increase the macroscopic friction in suspension. So now that we've studied a monovalent ion, we wanted to see the effects of ion valency. And for this, we use two other salts, which are calcium chloride and lanthanum chloride, so a divalent and trivalent cations. And we repeated the same protocols by measuring the swelling behavior and the avalanche angle as a function of the ionic strength. And what we observe here is that we distinguish two different regimes. One where we cannot notice any difference between the cations used, and another regime, sorry, where the particle swelling is considerably lower and where the friction increases drastically in the case of multivalent cations. And actually, in the case of lanthanum, we measure, we even exceed the value that was measured for the typical frictional suspension of PMMA particles. So if we measure the topography of these particles in presence of multivalent salts, we obtain this following graph with the surface roughness as a function of the ionic strength, and we cannot notice any significant difference, except maybe for the case of trivalent cations, where it seems that we reach a sort of a plateau at high salt concentration. Of course, this plateau can be a little bit discussed, but this behavior has been already observed with well-defined polyelectrolyte brushes, where, yes, at high concentration, you have a plateau reach of the length of the brushes. So, but what is important also is qualitatively, we observed for both divalent and trivalent cations the appearance of lateral inhomogeneities that can be seen as nodules, and these nodules are due to the presence of these multivalent cations, because these cations induce complexes between the polymer chains. And this is actually very typical when you have a phase separation occurring between the polymer phase and the solvent. So, and actually this lack of affinity between the polymer and the suspending liquids will promote cohesive effects between particles. And this is why you observe a more drastic increase in macroscopic friction when you use a divalent or trivalent cation. So a first summary that we can make here with rotating drum experiments is that we were able to synthesize stimuli responsive non-Brownian particle, and the rotating drum is adapted to small volume of suspensions, and it allows us to make relatively quick and easy characterization. And we were able to make correlations between AFM measurements and macroscopic friction. However, all these measurements were done in a quasi-static regime, and our goal after was to assess the whole rheological behavior with dynamic measurements. And this is at this moment that we used the capillar-vitron. So for the capillar-vitron, this was a collaboration with with EUSTI at Marseille, Aix-Marseille Université. And to use this device, we used bi-disperse suspensions in order to avoid crystallization during our measurements. And for this, so we used two different initial sizes of particles, so namely 60 microns and 40 microns, and their hydrolyzed versions, which double in size when they are in pure water. And we used a 80-20 volume ratio between the big and small particles. The solvent is pure water or salted water. The pressure imposed is between 30 and 40 pascals, and we explored a wide range of viscous number J. So firstly, we compared these two bi-disperse suspensions, so PMMA particles and their hydrolyzed version. Here I present you the macroscopic friction coefficient and the volume fraction depending on the viscous number J. And what we can observe here is that so when you are actually at very low viscous number, we can recover the macroscopic friction coefficients and the critical volume fractions of the suspension. And as I said earlier, when we are close to the jamming transition, the curves follow these fitting laws, and you have the values of mu c and phi c here, and the values of alpha mu and alpha phi here. If we look at mu c and phi c, we can observe that for PMMA particles, those values are relatively typical from a frictional suspension, and for hydrolyzed particles, those values are typical from a frictionless ones. And it goes the same for the alpha mu and alpha phi values. So for PMMA particles in pure water, they are around 0.5, and this is typical from a frictional suspension. And for the hydrolyzed particles, they are around 0.3, which is closer to a frictionless suspension. So with the capillarité, we are able to recover the similar trends that were found in the rotating drum. So this we were pretty happy with that. And what we wanted to assess after was the effect of salts on the hydrolyzed particles in the capillarité. And yes, sorry, but before, yes, we also studied the asymptotic behavior in pure water of the non-hydrolyzed particles and the hydrolyzed version. And we plotted the viscosities, so the relative shear viscosity and the normal viscosity of these suspensions as a function of the volume fraction. And as I said, we recover, so we have the scaling law and we recover the same critical volume fractions that we found with the previous graphs, and the exponent gamma is close to what was found in other experimental work for PMMA particles, so around -2 and around -2.8 for frictionless particles, which is in good agreement with the theory of de, for instance. So yes, then after this, we wanted to assess the dynamic behavior in the presence of salts for hydrolyzed particles. And these are the results we obtained. So I will guide you through these graphs. Here you still have the macroscopic friction and the volume fraction as a function of the viscous number J. And what we can observe is that, so the yellow and pink, and yellow curves correspond to the hydrolyzed particles in presence either of sodium chloride or calcium chloride. And what we observed for the macroscopic friction coefficient is that these curves follow the same trend of a frictionless suspension. However, the volume fraction follows more the trend of the frictional suspension. So this is a surprising result that that is still under investigation. And if we look at the fitting laws close to jamming, we find these coefficients. So yes, the mu c is more related to a frictionless suspension, but the phi c is more related to a frictional suspension. And regarding the alpha mu and alpha phi, both are more related to a frictionless suspension. So yes, we are still discussing these results because the value of phi c is kind of contradictory to the other results. But what we can make here is a little comparison with the rotating drum experiments that we had. So we have to remember that the working conditions in the capillaritron and in the rotating drum are different. So we impose a higher pressure in the capillaritron, and this could explain why we maybe don't have the same tendencies in both configurations. And actually in the rotating drum, we probably are more sensitive to adhesive and cohesive effects, because probably those cohesive effects are in the same order of magnitude as the set pressure. And actually we can observe it if you look at the results obtained with just PMMA particles in water. We can see that in the rotating drum, you might have a little bit more cohesive effect because the value is a bit higher than in the capillarity. And if you look at the case of hydrolyzed particles with salts, actually in the capillarity, we cannot observe any cohesive effects, whereas in the rotating drum, we used to measure much higher mu c's. So I have now come to my conclusions of this project. So what I would like you to remember from this presentation is that we managed to design stimuli responsive non-Brownian particles that are frictionless over a wide range of viscous number J, and that has not been observed before. And we were able to highlight the difference, the frictional state of the PMMA particles and the frictionless state of their hydrolyzed version in both pressure and impulse configurations. we were able to assess the role of the physicochemical stimuli on the hydrolyzed particles. And we observed that for the monovalent salt, the increase in macroscopic friction was essentially due to osmotic effects, whereas for the ion valency, and we also measured different conditions, so such as pH and temperature, and for all these cases, we found a phase separation occurring between the polymer and the solvent, which induces in the rotating drum much higher values of quasi-static macroscopic friction coefficients. So now the following steps that we would like to do is to link this macroscopic friction to direct microscopic friction measurements. So using an AFM method, and that would require to do so particle to particle friction. And so this protocol is under development. And another thing that we would like to study is the study of core shell particles, because so the reaction we did allowed us to observe different state of particle, and we were able to control the polymer layer that was hydrolyzed on the particles, and these will be of a good interest to study either in the rotating drum or also in the capillary. So with this, I would like to thank you for your attention and thank all the co-workers that helped me on this project. And I will gladly take your questions.
Thank you, Lily.
Thank you.
Very nice talk. Is there any question in the audience? Cannot see anything from the chat. Yeah.
Rahul? Yeah.
Hi, are you able to hear me?
Yes.
Hi, Lily. Thank you for the great talk. So I just have one small question. So when you run the experiments, how long is it for? I'm asking because like in the biodisperse system, so there are smaller polymeric particles. So when they stay long enough in water, they might swell up in size, right? So they might change the apparent volume fraction, solid volume fraction. So
so you're talking about experiments in the capillary tronc?
yeah.
So the experiments are about half an hour, but when I do the experiments, so the PMMA particles will not swell in water, that is for sure, but the hydrolyzed versions, of course, they swell, but they swell instantly. So I keep this volume ratio. When I calculate the volume ratio, I calculate them in terms of when they are swelled already, when they are swollen, sorry.
Okay, got it. Thank you.
And the experiment time is about 30 minutes.
Got it. Thank you very much.
There is another question from Dennis or Denise.
Hello, do you hear me?
Yes.
So I'm currently working with Chico, which is also in the room, and we are working on a very close system, which is basically the same than you, but with dry granular matter. And what we observe is that, for example, you can have a pressure dependence, because in your curve that you show in your mu of G, normally all the curve collapse together. If you change the pressure or the viscosity and stuff like that.
Yeah.
And here, did you try to change the pressure, the viscosity of the fluid to see if all the data collapse or not?
Yes, so actually, yes, we did vary the pressure range, and we varied it from 10 to 1,000 pascals, if I remember well. We didn't observe much difference in terms of mu C. So, and we did that for the PMMA particles and the hydrolyzed ones, and in presence of salts, and we didn't observe much difference. But maybe that's because the pressure we applied was too high compared to the adhesive effects that we wanted to observe.
Okay,
so ideally, we would like to apply, I don't know, maybe in the capillary tronc, if we're able to apply a pressure of 0.1 Pascal, that would be ideal, but it's not feasible yet. So.
Okay, and do you have some work published or not? Because I didn't manage to find any preprint or whatever.
So no, not yet. So I only have my my manuscript that is not published yet, and we are writing. So the article are in progress.
Okay. Thank you.
So we have other two questions for now. Giovanni, please.
Oh, hello. Thanks for a great talk. I think probably a couple of stupid questions. So just giving on this slide, 28.
Mhm.
So is the volume fraction you're showing on the right panel somehow fixed by you in the experiment, or you are calculating this as a result of?
So the volume fraction is not fixed. Well, I mean, since we can adjust the volume of the liquid, this is why we vary the volume fraction during the experiment.
Okay. And actually, my second question is related to both panels. So since the curve seems to be quite same shape, I say power law essentially, but rescaled. So is there a smart way of collapsing these curves? And if so, what parameters should be used? Because again, they have similar shapes, but some point might collapse into one, say, universal sort of shape.
What curve would you like to collapse? I'm not sure I understand your
Oh, the
question.
one on the left, the green one. Of course,
Yeah.
it's higher macroscopic.
So actually, the green one, the curves seem similar, but they don't have the same exponent. The green curves doesn't have the same exponent as the other ones. So when you have a frictional suspension, the alpha mu here should be around 0.5. And when you have a frictionless suspension, so the other three curves, the alpha mu is more around 0.3. So no, they shouldn't. I don't think they should collapse.
So essentially, you're changing just the alpha mu, right? But the power law is the same. I mean, same law, but different exponents, right?
Yes, exactly. Yeah.
That's what I'm saying. It's still power law. There might be a way of normalizing the power law in such a way that you have a unique power law. You know what I mean? Because it's not that you have an exponential and a power law. They are completely different functional behavior. It's the same functional behavior, just rescaled. So I was wondering if there is a way of collapsing them, right? Just don't have the same power law, essentially.
Yeah, true. To be honest, I haven't really thought about that. Maybe, yeah, we could find a unique sort of a master curve, you say?
Yeah, essentially the mu c and the alpha, the a, all the parameters, if you properly normalize them, you collapse into a universal sort of power law. But again, that's easier said than done, but of course.
Yeah,
Anyway,
yeah,
thanks.
but
That's all right. Thanks.
Okay, another question from Chico.
Hey,
Or Kiko.
can you hear me?
Yeah.
Hello? Yep. Hi, Lily. Thank you for the very nice
Kiko.
talk. So I have two quick questions. One is regarding this plot on your left.
Yes.
Because your frictional curve, it looks like a non-monotonic, more or
Yes.
less. So this seems to be related to like frictional hysteresis because the maximum static friction is higher than the lower dynamic friction, more or less. So the question is, do you see some kind of hysteresis in the drum as well?
So actually, no, we don't see hysteresis in the drum, surprisingly. And so in the drum, the speed I apply is made to have a like we have a continuous flow and we are in the quasi-static regime. And when I lowered the speed, we still didn't observe any hysteresis actually. So yeah, this was kind of surprise for us, but and here actually so you could relate it to hysteresis, but discussing with the Marseille laboratory, they also related that to velocity weakening maybe. Yeah.
Okay. And the other quick question is, when you do in the capillary tron, the bidisperse to avoid crystallization. Since you change a bit the size with a different size ratio, do you think there is some effect of segregation happening? So I don't know, have you tried to change the proportion of large and small particles to have the same thing, or you think it doesn't matter?
So we didn't change the proportions, but we chose those proportions because it was in the literature. What it can change is the volume fraction of the suspension, the maximum volume fraction.
Yeah.
But with this ratio, it didn't impact this much the values.
Okay.
I'm not sure if I answered your question.
Yeah, sure. Yeah, that's it. Thank you.
No problem.
That's what, like a 1.2 aspect ratio, right? 40 and 60.
Sorry?
What's the aspect ratio? That was 60 and 40, right?
Oh, it was
And the double
80-20.
Oh, 80-20, sorry.
Yeah.
Okay. Oh, that's between the big and the small particles. So
Yeah,
that's
yeah,
okay.
Oh, and the ratio between, you mean
Yeah, the
the
particle
size ratio of the particles? Well, it was a
60 and 40, okay.
Yeah, 60.
That's 1.5, 1.5.
Yeah, exactly.
And the double size for the HP 60 and HP 40, right?
Yes.
Okay. I don't know if Denis has another question or they no, okay. I do have another question.
Mhm.
So it's more of a comment I want from you actually, because you said that the reason why the HP6 and HP40 particles are frictionless, it's because they have these negative ions on the outside, so you have repulsive forces, right?
Mm-hmm.
But so I've done simulations, and for me, that's not how I would define frictionless. That's just some repulsive forces. So if I can imagine to take the same particles and put them under a different shear stress or shear rate, of course, I might overcome those repulsive forces. What do you think about it? Do you think that happened in the capillaritron? I don't think that could happen in the drum.
Well, we didn't observe. I mean, what you are asking is that maybe this suspension is not really frictionless. It could become shear thickening.
Yep.
I guess. We didn't observe this in the capillaritron. Surprisingly, we were expecting this result, but I think that in pure water, this electrosteric repulsion is so high that it really prevents the particle from touching each other. And this has, so we kind of related our experiments to some work that was done on hydrogel surfaces which were studied by Gong and al. And they observed very low friction coefficients as well, even with applying like high shear stress.
But do you expect then to see a finite a higher mu c under AFM, or in that case you really take your particles and you put them to touch, you push them to touch each other, right?
Yeah, well, in AFM it will be the value will not be really comparable to the macroscopic friction because we will
Sure.
measure mu p. So,
Sure.
but yeah, definitely the value can be. I think usually the mu p is a bit lower than the macroscopic friction coefficient. But
Might be, yeah.
Yeah, because you impose a sort of a oscillatory movement. So I'm not sure. Like these are we didn't even start the experiments yet because we are kind of struggling with gluing the particle to a cantilever, and because these particles swell, it is kind of a challenge to glue these kind of particles.
Well, I definitely look forward to your results.
If I have time during my postdocs, I will definitely go further into these experiments. Yeah.
Are there any other questions? Well, if not, I thank you again, Lily. This was honestly a great work, and thank you for sharing it with us today.
Thank you very much.
Thank you,
So
Lily.
I'm gonna share my screen again.
Mhm.
And I'm gonna stop also recording if I